Hello guys, and welcome to this new Excel video. In today's video we are going to be seeing electromagnetic induction, and specifically we are going to work on Faraday's and Lenz law of electromagnetic induction. But before we get started, I would like us to make a brief recall on magnetic flux, as it's going to be very important in understanding what we are going to do in this video. So what is magnetic flux? Magnetic flux is defined as the number of magnetic field lines that pass on a unit surface area, and is given by the formula delta phi is equals to BA cos theta. If you want to consider a small diagram that will help us understand this notion, we can consider this diagram where these lines represent the magnetic field of a particular density, which is measured in Tesla, and A, this figure, is the surface given by A. Now to get the magnetic flux density of this surface, it is simply the product of the magnetic field intensity times the area times the cosine of the angle between the magnetic field lines and the normal to the magnetic field lines. That is the area between this line and the normal to this line, this normal. So is this area that you take to be a theta, and this other area here, you can call it alpha. So to get the magnetic flux density is a product of the magnetic field intensity times the area of this surface through which the magnetic field lines are passing, and all that multiplied by the cosine of the angle between these field lines and the normal to the field lines. And you should take note that if the angle between the field lines and the normal is equal to 0 degrees, then simply your phi becomes BA. So you have, in this case, you have a maximum magnetic flux that is passing on a surface when it is parallel to it, since the normal will be perpendicular, and we all know that. So with this notion of magnetic flux, you will now be able to understand what electromagnetic induction is all about. So by definition, electromagnetic induction is a production of an electromotive force or an EMF across an electrical component due to changing magnetic flux. Okay, so with this notion, you have to understand that in the early 19th century, that is in 1830, it was discovered that it is possible for you to produce a current or induce an EMF in a conductor simply by varying the magnetic flux around that conductor. To better understand this definition, we are going to use the following sketch. That is, when you have a magnet with a north and a south pole that is brought close to a coil which forms a closed circuit with a galvanometer attached to it. When this magnet is brought close to this coil, the magnetic field lines of the magnet are going to induce an EMF on these coils, and due to that induced EMF, there will be a current flowing. There will be a certain current flowing and an induced EMF. That's, you will see the arrow of this galvanometer deflecting, showing that an EMF has been induced due to the presence of the magnet. So the relation between the induced EMF in the conductor and the magnetic flux of the magnet in question is given by E is equals to delta phi by delta T. Delta phi simply means is the change in the magnetic flux over time. Now, this is the case where the number of turns or the number of coils here is 1. In the case where there are 2 coils, here you have 1 coil, 2, 3, you can have up to n coils. In the case where there are n coils, the induced EMF will simply be n d phi by dt, where this n now represents the number of coils. With this notion, we can venture into seeing what Faraday's law is all about. So Faraday in the early 19th century found that when a magnet is brought close to the coils of a conductor, it induces an EMF into it, and from there he came up with the following law. Faraday's law simply states that the induced EMF in a conductor is directly proportional to the rate at which it cuts across the magnetic field lines of a magnet. We can represent this using 2 bar magnets with the north and the south pole. We know that the magnetic field lines always flow from north to south pole. So if you have a conductor that cuts across the magnetic field lines of this magnet, you are going to find out that the induced EMF in this conductor, the induced EMF is going to be proportional to the rate at which it cuts across the magnetic field lines. That is going to be proportional to dphi by dt. Now, depending on the number of this conductor from Faraday's law, simply it will be that the induced EMF will be N delta phi by delta T. So this is a statement of Faraday's law of electromagnetic induction. Now, with this, we can go further to Lenz law. Lenz law is simply a complete statement of the laws of electromagnetic induction. So we are going to see Lenz law. So after Faraday came up with this law, it was later on found that when you bring a magnet close to the coils of a conductor which forms a closed circuit, the induced EMF due to the magnetic fields of this magnet, is going to oppose the action that is producing that EMF, which means that as you are bringing this magnet into the coils, the force that will be produced, which is that EMF, is going to act so as to oppose the force with which you are bringing a magnet. So Lenz law simply states that the induced EMF in a conductor will always act so as to oppose the changes producing it. So it is writing it, you simply have epsilon, which is the induced EMF, is equal to negative N dphi by dt. So what you should note here is this negative. This negative here. This negative now represents the direction in which the induced EMF is going to act. Okay guys, we have come to the end of this video. I hope you like it. If you have any suggestion, any comments, don't hesitate to leave them below. And don't forget to subscribe to our YouTube channel in order to get notified in case of any new video that we might upload. Equally, do not forget to follow us on our social media platforms, especially Facebook. Thank you.